parameters, but I'm increasing LER. And it doesn't look like much, but there's more to come. If we increase it to 6 nanometers, there's roughly a 20% increase. And 6 nanometers is something we've chose arbitrarily just because of what we found in the literature, and seeing from the previous talk, it seems to be a good number as well. But we can, hopefully we can improve this given the ITRS targets. Now the next thing is, obviously 0.95 and 0.4 I mean, considering this is ideal, we want to try to get a nominal idea as to what could be going on. So we have used the values of 0.26 and 0.34, and this is just the average of these numbers here, okay? But we have an LER of 6 nanometers. So what happens if we compare this to ITRS values? Well, using this and comparing it to ITRS values, now we see an 87% increase towards the end of the roadmap, considering LER and this new model. So what about, is there like a really bad upper bound that we can consider? And this is going to be my last slide for the talk. One of the values that we saw was P equals 0 and R equals 0.5. With 6 nanometers of LER, you're looking at about 140% increase towards the end of the roadmap. So clearly there's some insight here physically with this model. And now we can actually see where or how we should adjust maybe the targets for the end of the roadmap, considering the LER. And now that we've modeled this a little better, modeled resistivity a little better physically, we have better insight as to what can happen as we get to the end of the roadmap. So to conclude, we've developed a physical model that's been carefully derived. Is now a function of LER, grain boundary reflectivity, sidewall specularity. We've calibrated this model, and we are able to predict sensitivity, especially towards the end of the roadmap, where LER becomes a significant portion of the effective line width. And we see, using our parameters, and 6 nanometers of LER, we're seeing an 87% increase in resistivity projections over the current ITRS projections, especially towards the end of the roadmap. And given the ITRS 2007 target values, you know, one of the things that you kind of have to assume that they're almost completely elastic sidewalls collisions, but more importantly, they're assuming no LER. So we have to consider LER. And clearly, novel processing and material integration techniques are going to be needed to meet these aggressive targets by the roadmap. This concludes my talk. I'm open for any questions. Thank you so much for your attention.
Great, thank you for the depressing perspective. Anyway, we're now open for questions. Any questions? Okay, I had a question about the length scale of your LER. You have a fairly long length scale. If you have a very small length scale of LER, at what dimensions will it start impacting your scattering parameter P, your specularity parameter? Do you have any comments on that?
So the question was that if I were to have a smaller length scale, and I want to know if my P value would go up or not.
Yeah, at some smaller scale, the LER should, well, presumably will have an impact on your P value. I'm just wondering with the length scale, do you have any perspective on that, when they will actually start interacting?
You know what? No, I don't have any insight into that, given that the main assumption behind the model was to make it. But clearly, obviously, if you were to look at a more discrete version of this, you can actually make a prediction. Yes, the sidewall specularity should go up, just because you are going to have higher interaction. You're essentially increasing the length of the wire by shortening and shrinking the compressing it. So, yeah.
Any other questions? Audience is too depressed now.
So I didn't catch the R parameter for the reflectance probability of countering a grain boundary. As you shrink down, was there any accounting for the probability of running into R more often? In other words, the grain boundary density as you shrink down? Was there any assumptions built into the model on what would happen to the grain boundary density?
Okay, all right. So the question is that for grain boundary scattering, what were our assumptions for the interaction with the electron and how often? Okay, so let me do this. Okay. This will be okay. So when we talk about D, this is the distance between reflecting planes that was originally found by the Yeah. And the assumption is based on some papers that I've read, is that you can actually make this D value a function of the alignment. And some have found it 1-to-1. So that's kind of the assumption, is that this R parameter, even though it is, you still have to, you can't directly measure that. I guess that should be the answer for you. You can't directly P and R values. So subsequently, given this physically based model, we try to choose the values that are best fit. And sometimes there are only 2 values, one for R, one for P, that actually do work for particular data sets. So that's just one thing just to keep in mind. But this right here is an assumption that's started to be built upon in the past. So that's just something that you. Yes.
Using the number model, you basically assume that the resistance of the line is the sum of the individual segments, right? Just circulate the resistivity. That implies that you also assume that the correlation length, or the size of the wedges from the previous talk, is much larger.
Right, they're very
with the line.
Right.
So you didn't take current crowding into account. If you would do that, how would that affect your results?
I'm sorry, you picked a line.
So you didn't take current crowding into account.
Counting.
Crowding.
Crowding. Oh, crowding? Okay.
Current crowding.
Right. No, I didn't. I did not. So as far, and this is kind of similar to your question, is, you would expect obviously more interactions with the sidewall, because there's, the sidewall's curving in and that electron wants to go down the conductor. So yes, you would actually see probably a jump in the interaction between the electron and the sidewall.
Yeah, I would assume that the resistance then is much closer to the minimum line width instead of the average line width, taking the LER into account. So it would be worse.
It could be worse, yes. And I think the problem is that what you have to consider is that, yes, this seems like a very ideal model. And what you have to do is know that since it's a closed form model, and if you consider an overall averaging effect that's going on along the length of the conductor, it's kind of like a good assumption to make based on, if you're talking about long lengths overall for a system. So I hope that answers your question. I'm not sure.
Yeah, okay, thank you.
All right, I think we should thank our speaker. This actually concludes this session, but we do not have a break, so don't go out there now. We have a concurrent or a immediately following session. Since we don't have a break right now, I'm going to actually ask the presenters to come back at a 3:30 break for questions. So if you have a question from one of the speakers from the previous 3 talks, please try to find them here at 3:30 at the podium. Okay. And our next session.